Great. How many people have been part of a job interview, on the receiving end of a job interview, where they ask you a bunch of trivia questions about the programming language you're going to use or the YAML that you're going to write? Most people, yeah. And when you started that job, did that make you magically productive? There's so much more than the programming language that we need. We have to figure out new people to work with, new deployment processes, new linting rules and PR procedures, and a whole new code base. So it's kind of sad that in our interview process, we get stuck on measuring knowledge stock, when what we need to do our work is knowledge flow. We need to learn and even unlearn things as we go, because we're part of a changing system. That's kind of the point. We change software, we change the system. And we need to change with it. So this talk is also titled, How to Learn More While Doing Your Job. Because today is a rare day when we get to mostly just learn things and meet people and talk about stuff. But most of the time, we need to learn while we're doing the work. And that's why I care about experimenting in the socio-technical system that we're actively in. Now, I'm Jessitron online, and I work at honeycomb.io, which is relevant because at Honeycomb, we have company values on our website, as you do. And one of them I find particularly interesting. Everything is an experiment. Blah, 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 blah. It's what we learn that matters. And I like this value, but it's not really what we learn that matters. It's not the only thing that matters, because our objective is to get software in the world, and to do that, we have to make money from the software. And so there's all kinds of other stuff that matters, but what we learn also matters, and at least we acknowledge that in our company values. But there's a couple of things about this value that puzzle me. One is this Erlenmeyer flask. Why is the water going up in a wave? Like, if it were a slant, that would make sense. Maybe the flask is spinning and you've got the centrifugal force going on, but the wave, whatever. I'm not a designer, and it's definitely cute. The other thing is, what really is an experiment here? Because I hear people at work talking about experiments all the time, and like I was a physics major in college, and so I have an idea of what an experiment is, and it's very rigid. And that's not, sometimes I do that at work, but not very often. And then some people try to make everything into an A/B test, and that is not the thing. Do not A/B test everything. So what does it mean that everything is an experiment? And after much struggle, I've finally come to think that one reason I can't express it is that the definition of experiment is not the same everywhere. Today I'm going to talk about 4 different definitions of experiment, all rigorous in different ways, that are appropriate to different levels of the system. A spoiler, it comes down to everything is an experiment if we look at the results. If you look back on your time at DevOps Days and think, it was really good that I met that person. I'm glad I stood in line at the restroom and actually talked to people. Then you've learned something, and that makes this more of an experiment. You'll do something different next time. But right, I have actually a lot more experiment-y properties, because my work isn't entirely an experiment, but I want to make it more experiment-y. Yeah. All right, back to physics. So canonical high school physics experiment. You draw in your lab notebook, you draw the apparatus, and here we're going to have a ball rolling down an inclined plane. We're going to release the ball and time how long it takes to, bam, hit the block at the end. Okay. And we're going to do that several times and write down our results, and then we're going to compare them with the theoretical results from the acceleration of gravity and stuff. And that's a real experiment. It starts with stating our expectations. So we do this with the theory that is provided by teacher. So in this case, we didn't have to put too much thought into it. And then we take one action, which is rolling the ball and timing it. And oh, look, we varied the incline of the ramp. That was one thing, too. And then we look at the results. And now in this case, we look at the results. We find that there's a 55% error. And we're so happy because the error was consistent. And then in a scientific experiment, you can look at those results and update your theory. Now, that didn't happen here. In this case, this was a toy experiment. It was not experimenty in the sense that I want, because the people did not learn anything about physics, well, about the acceleration of gravity anyway, from this experiment. But I'm going to, because I don't live, when I'm writing software, I don't live in nearly as stable a world as physics students do. So now we're in the land of systematic testing and measurement. And this is like the canonical science experiment where you have control over the environment and you're in a world that's the same all the time and all over the globe. And for us, systematic testing and measurement applies when I'm working with a program on my computer, like a single process on a single computer, and I can actually test it and expect it to behave deterministically all the time. And if it doesn't, I restart my computer. Because that restores it to a more controlled environment, see? Yeah, okay. So we start with stating our expectations, and a beautiful example of this is TDD. So if you're doing test-driven development, you start by writing a test. Don't read this code, it's just a test, I promise. You start by writing a test, and then you run the test and it fails. Okay, and then the fun part is instead of updating my theory about, oh, well, I was wrong, I shall change how I think about the world. No, I get to change the world. I get to change how the world works until my theory is correct and the test passes. And this is why I love being a software development, and I'm so glad I switched from physics. Until it doesn't, of course, and the test fails when you didn't want it to, and you look at the results and you're like, what? And at this point, I have one piece of advice. Read the error message. Read the entire error message. And I always forget, and what do I do instead? I add a console.log. And that's also interesting because when I add a console.log, I am creating a scientific instrument. We get to do this in software. We want to know something about its inner workings, we make it tell us. That is so much harder in biology. They're like hurling genes at seeds and trying to inject something that glows under black light so they can see whether it worked. So much harder. So another reason I love being in software. We get to build our own scientific instruments. And scientific instruments are an important part of experimentiness. A scientific instrument is anything that we build in order to learn about the world. This could be a microscope. It could be a marker gene. It could be a questionnaire. That's called a scientific instrument, which is really confusing unless you're in the social sciences. But it's a thing. And we get to build those in software. The debugger kind of like negates me having to build scientific instruments, because if I hook up the debugger to my tests, which I never do because, my gosh, that's hard in VS Code. But if you hook up the debugger, then you have like this magic scientific instrument that shows you everything. So prize to the debugger as most versatile instrument in the level of systematic testing and measurement. There's one more piece to this that I want to add before I move on to the next level. When we drew this apparatus, we were describing the world in which this experiment took place. Under which circumstances can you expect to reproduce these results? And we do this in software now, in our Docker files, and in our Terraform, because we don't work in the same world as each other. I mean, your immediate teammate that you're working on the same system with the same development configuration, hopefully, most of the time, until it doesn't work for you and it does work for him, and then there's a whole, but every programming language is a different world. Every version of every programming language is different, every set of libraries, and then there's the runtimes, and then there's all the browsers that your code is running in on other people's computers, and we do not all work in the same world. So we do the best we can to describe the situation of where we can expect this code to work as it works for us. And that's been a major progress in the last 15 years or so, being able to describe the situation in code. And that's really important when we go to scale up, because we've got the software running on our computer, we can do systematic testing and measurement. But then you put it in production. And yes, we can do some testing. Do test in prod, please. Your customers are. Look at the results. But it's more than that. It takes more than that. This is the realm of measure and adjust, because not only do we need our code to work as expected, but we need to check that the whole system is still working as expected and working fast enough and smoothly enough and generally functioning at least as well or better. And that takes looking more widely than just what our code is doing. I have a story about that. So Martin Holman at Honeycomb was doing something with user sessions. And in the course of his work, he noticed this graph, which is the free storage space on our session database. And it's going down, and it's going down at about 5 gigs per month. And it's currently at 10 gigs. So in 2 months, we're going to run out, boom, no more sessions for us. So he flagged that. He was surprised. And he was like, wait a minute. What is going on here? And he tried deleting a bunch of sessions, and databases are mysterious, so that didn't help. But in any case, we need the rate of this depletion to change. So he ran a query in Honeycomb, because we use Honeycomb to monitor Honeycomb, and he checked all the places where the database query contains sessions, and everything that you add to your observability, every attribute on every log or every trace span is a scientific instrument. And he was able to find the inserts. We want the inserts here. So he narrowed it down to just the inserts, and he's looking at the count of those. And this says that every hour, we're getting about almost 20,000 sessions inserted. We do not have 20,000 concurrent users. We have maybe 2,000 during the day. On a weekday, it is not steady across the week like this. What is going on? That looks wrong. So he clicks into one of these and he gets a trace, and it's like no user in session. Well, why are we creating a session record at all if there's no user in it? And the answer is this middle span, the push redirect URL, because if somebody, say they click on a link in Slack to go look at a graph in Honeycomb, and then they get redirected to the login page, we need to store where they were trying to go so that after they log in, we can send them there. So where's this person trying to go? Slash. Well, that's boring. That's the default. What if, and also every robot who hits the page is trying to go to slash. So what if we just didn't save these? And then we're counting. How many of these sessions are slash? And it's 6 million out of 6 million and change. So yeah, what if we just didn't save these? And so he deployed that, and you can see the insertions into the session database. See, this is what I love about observability. This is why I work at a Honeycomb, because you can see what you're doing even in the back end. I don't have to depend on a UI to see what I'm doing. I can make my software tell me. So that was good. And then he went back and he counted, okay, what redirect paths are we seeing now? And the most popular one is some customer doing something they're not supposed to do, and we can address that separately, but it's 20,000, not 6 million, and we're okay. And then the rate of free space going down, right? We got a big jump in free space now that we have fewer insertions, and also the line is pretty much horizontal. We're not going to run out of space here in the time span that we care about. So win. And this teaches me that when you're doing an experiment, or even not, look at the results, especially the ones you didn't expect. You know, in the physics experiment, we looked at how long it took the ball to hit the block. But did we care about how it hit the block or whether it jumped, or I don't know, that one's a really hard one to imagine surprise in. But in software, we get surprised all the time. And appreciate that, because it's the surprise that really lets you update your theory. And updating our theory that's the learning bit. That's the knowledge flow. Oh, and prize to observability for most versatile instrument at the level of production. Yeah. So we want to look at the results. And one more thing, Martin started from an observation. In his case, he happened to notice that free space was going down. If we can be explicit about why we're doing this thing that we're doing, that makes it more of an experiment. He started from an observation that something in the world was not as he would prefer it, and he started with an intention to change that, to make the world more like he would prefer it. And that gets even more important when we get up to the next level, which includes users. So here we have the people or software using our production software system And once we include that, no Docker file is going to describe this environment. We are not going to have a whole lot of control. There's a lot of randomness involved. And therefore, the gold standard of experiments at this level is randomized controlled trials, like in medicine. That works in medicine. We're going to check the effects of what we do. That's what we can do here. Check the effects, and ideally, two realities, otherwise similar. We do something to half of the people involved and not to the other, and we see what the difference is. For instance, here's a study that was cited by my doctor 15 years ago when I got tired of having nightmares about having another child, and asked for permanent birth control, and he was like, well, this one is really safe. They found no side effects and no pregnancies in the whole study. And so sure, I got that, it's working out. Here's a lovely example of a randomized controlled trial in software. So at Honeycomb, we use Lambda. We use a lot of Lambda. It is by far the top item on our AWS bill. And like 3 or 4 years ago, AWS released Lambdas running on ARM chips. And they're supposed to be faster and cheaper. And faster also means cheaper, so that sounds like double cheaper to me. And that is a win. So Liz Fong-Jones set up an experiment. These are in early release, right? Not everybody is using them yet, and she's actually helping AWS evaluate these chips. And here is 50% of our Lambdas running on ARM and 50% on AMD. So the newer chips are the orange line, and you can see this is the P99 and the P50. You can see the orange line is mostly above the purple line. That means slower. That means bad. If we zoom in on the numbers, the P99, so the worst case is way worse, 2.5 seconds. And the average is also higher, not by as much, but by enough that it negates any cost savings, because slower is more expensive. Liz flipped the feature flag, or adjusted the feature flag, so that we're running 99% on AMD, 1% on ARM. We'd notice if we broke it, that's useful, but we're sticking with the old chips for now. But she didn't stop there. Oh, Scientific Instrument is the feature flag here. She didn't stop there. She looked into, okay, why? We had a hypothesis that this would be faster and cheaper, and it was not faster and not cheaper. And it's more of an experiment if you're willing to back up, reverse the change, if you can, and try again. Because just because it didn't work now doesn't mean it never will. Jerry Weinberg has a saying, everything new is broken. And it's broken because the rest of the system isn't ready for it. So Liz looked into why were these slower, and one was capacity constraints. We like to spin up 10,000 Lambdas in about 10 milliseconds, and they didn't have that many chips available. And so the AWS fixed that eventually. Another thing was Golang wasn't ready for ARM in the sense that the version we were on didn't have some optimization. So we moved up to 119 pre-release. And then there was the compression library that we use, which is a lot of the compute that these Lambdas are doing, is decompression and compression. Decompression it wasn't ready. It was still using the old instruction set. So Liz made a pull request to that library in Golang and got that updated. And once all these parts of the system were more ready for the new chip, now we are running 99% ARM and 1% AMD, just to make sure we don't break it. And zooming in on the numbers, the one that matters is the cost. And the ARMs are significantly cheaper than the AMDs. So they're about the same speed, but they are cheaper, so win. Not double cheaper, but we'll take it. So Liz was willing to back up and try again when the system changed. So just because you tried pair programming once and you hated it, doesn't mean pair programming will never work, even for you. There are many different situations that you might be in, and every consultant and principal developer will tell you that it depends. And it does. So if we can notice the situation and start to determine what it depends on, then we are advancing our knowledge. Okay, but this involved users. This level of the system is supposed to involve users, and that example didn't. So here's one that does. Here's a proper A/B test. The green team was the growth team, and their job is to help people who get into Honeycomb get value from Honeycomb. So here's the theory. The theory is people make an account, and then they instrument their production software, and then they send us some data, and then they get clues. But the middle in there is a little fuzzy. But the first theory is, well, they need to run a query. If they run a query, they might get some clues. So we want them to do that. And we made some observations. We look at, we start from observation. And that's an amplitude. Amplitude is showing people's flow through the UI. And they found that a lot of people got stuck here. They got to this settings page. This is not useful for anyone new. This is like super advanced stuff. Nobody cares about the default granularity when you haven't even run a query yet. Why were they getting there? Well, you look at the nav bar, and this is like item number 3, and its name is data sets, which sounds like tables, accurate, and you'd think you could get your data from your tables. Well, you don't. You need to hit new query. So the growth team said, how about we move that down and rename it to data settings? And then we'll move some useful stuff up and some other boring stuff down. You don't need history yet. You don't have any. Oh, and we'll rename new query to query because that's less frightening. I'm not a designer. So they did this. And next, they need to describe the situation. And the situation for this randomized controlled trial is new accounts created at the free tier. We have a free tier at Honeycomb that's actually useful. And it's also useful to the customers. But it's useful to us because we can experiment on them because there's no sales rep saying, don't mess with my account. So half of the people who created a free tier account in June saw the new nav bar forever, and the other ones got the old nav bar. And then they can measure the difference. And sure enough, way few people went to the data settings page, progress. And more people did useful things like boards and SLOs. And did they run more queries? Well, yes, but it's not statistically significant. So there's a better than 1 in 20 chance that this was just random. But it's not worse. So the green team, shout out to feature flags as the most versatile instrument at this level of the system. Super, super useful. If you have feature flags in place, you can do this. Otherwise, everything is hard. But the green team took these numbers back to the rest of engineering and showed off the results, and everybody was happy. Oh, obviously, we need to update the nav bar for everybody. Let's make this permanent. Let's delete the old code. Did we ever do that? And just show the new nav bar. Now, I don't think the PM on the green team was at all surprised by these results. I don't think anybody was shocked that renaming data sets to data settings and moving it down caused fewer people to get stuck there. But every item on that nav bar is owned by another team at Honeycomb. And nobody wants their nav bar item moved down, right? Until you present them with evidence from an experiment, and then obviously we're going to do the correct data-informed thing and move the nav bar this way. And so sometimes it's not your theory you're updating. And our researcher, Justin, who's I think out at the booth right now, points out to me that sometimes you're doing the experiment to help the rest of the system believe you. Because as an expert, it might be obvious to you. That's the thing. But we don't work alone. It's not just us. There's, at least past Series A, there's a lot of other teams that are all working on this software. And this is the level of the system that I'm really interested in. The socio-technical system of development teams and the software we maintain. And this level of the system is a symmathesy, a learning system made of learning parts. This word was coined by Nora Bateson, anthropologist, from the Latin sim, together, and mathesy, learning. It gives us a way to distinguish between a system like a program on your computer, that if you understand all the parts and their relationships with each other, you can really predict what is going to happen. That's not true in an ecosystem, and it's not true in a person or a family, and it's not true in our teams. And then I include the software in the team because the software participates in this learning. It learns from us because we change it, that's our job. And we learn from it when it throws an exception through our observability and our tests and the data it changes, and indirectly through users complaining about what it just did. And with more scientific instruments, like feature flags and observability, we can make the software a better part of the team, a better participant in the flows of learning, in the knowledge flow, in the symmathesy that is our socio-technical system. So that's what I like. That's what I want to accomplish. But here's the thing. Randomized controlled trials do not work. So now I'm citing a literature review of a bunch of randomized controlled trials in the social sciences. Megan Stevenson is a professor of law and economics, and she points out what's subtly obvious if you really look for it, that when it comes to the type of interventions that you can do a randomized controlled trial on, something simple like just the nav bar, social change is hard to engineer. By engineer, she means move one lever, do a thing. So she's looking at intervention programs like you've got people who are getting out of prison and you help them get a job. And it turns out that stabilizing forces push people back toward the path they would have been on absent the intervention. The social pressures, maybe you gave them a job, but they can't get there because they don't have a car, they need childcare, something like that. If you give people money, they wind up spending it on people who are even worse off. The stabilizing forces in the rest of the system push people back. In software, that might be, oh, we pushed really hard and we got a day to work on technical debt. And in that day, you indeed managed to submit some pull requests, and then the feature work floods back in and you never get a merge and the branches are stale, it's gone, it's lost. Yeah, and a success achieved in one setting may not port well to another. So if you were on your team, you decided to try a thing and it worked really well and you liked it, then you try to impose that on some other team and it wasn't their idea and it's not the same situation and it doesn't work. Shocker. The successes in one settings don't port. And this feeds, Stevenson cites the iron law of evaluation. The expected value of any net impact assessment of a large-scale social program, you scale it up, you spread it out, the net impact is zero, because the rest of the system wins. So, randomized controlled trials are too limited. They only go to small changes, and you try to generalize that, and it's not a thing. And that Escher study, this is the follow-up study from 10 years later, when they found actually some people have nickel allergies, and there was a pregnancy, and it wasn't a good one, and they took it off the market. Now, I'm fine, I was lucky, but a friend of mine was not and had major surgery, and it was a major disruption, and that sucked for them. So what we learned from this is to keep looking at the results. After the end of the quarter, continue to see whether, in my case, that blog article still gets views, or whether that change is still working for customers now that it's not new and flashy. Are they still getting where they need to go from the new navbar? Yeah, keep looking. The bigger you get in the system level, the wider system you're trying to make change in, the slower that change is going to be, and the more surprising. But this is the level that I really want to make change in. As an example, what does work at this? One example of things that does work at the socio-technical level, domain-driven design. Now, this book it's 20 years old now, actually. But domain-driven design is about using the same language consciously in our mouth words, in our documentation, and in our code. And it's about deliberately agreeing on definitions and the scope of those definitions. It's very explicitly scoped. So this is a programming paradigm, software development, not just programming, that is deliberately designed for a socio-technical system. And I bring that up in particular here because y'all have the DDD conference. This is the one in the US. It's spectacular. I wish they would rename it to Software Architecture and Socio-Technical Systems, because that's what it's about. It's named Explore DDD. It's fantastic. It's in Denver in the spring. Highly recommend. Another place that I learned about techniques to work in socio-technical systems, to do experiments in particular, is from Brené Brown's books. Now, Brene Brown researches wholeheartedness, and she does this by interviewing people. I think she started with like shame and got to vulnerability and then wholeheartedness. She's using a technique called grounded theory. Grounded theory involves interviewing people and actually listening to the answers, okay? And not just, please categorize yourself in this dropdown. And on a scale of 1 to 10. No, it's actual people listening to the answers and then looking for patterns very deliberately and methodically in the answers from multiple people. In grounded theory, we do start from some observations, and we start with a question, but then we really listen to the situation. You'll never specify it fully. And then we look for new questions, new, more interesting questions, and then we go back and talk to some of the same people and some different people, and we like get farther. And then, in grounded theory, you're not taking action. You're not trying to fix these particular people. So that's different from us. So I have to go to another level, and that's action research. At the sociotechnical system, action research means working in a system that you are also trying to change. Our purpose here is to learn about the system in order to change it, and while we're doing that, we're going to learn more about the system and be able to change it better and so on. Action research is what we want here. It's been a thing since the 50s, super big in education these days, but I think it's what we want. And the thing about action research is it's a spectrum. If you look at the observe, plan, act, reflect, then at the practitioner level, we're mostly interested in acting, and people kind of minimize the time they spend on everything else. But this is your junior level. And as you grow, and as I get older, and I'm a manager now, I spend a lot more time observing and reflecting, so I'm closer to the action researcher end of this spectrum. So more experimenty, still getting stuff done. So maybe we take one action, and then we look at the results, all of the results, for a long period of time, and not just numbers. Okay, when someone asks you, how will we measure this? Please replace that with, how will we notice this? How will we notice that this is working? How will we notice that this is not working? Sometimes that's quantitative, but also it could be things you hear in conversation and things you receive in a Slack DM and things you get from asking people a question. And then our goal is, I should change this to update our theories, because in a social situation, it's always more complex than one theory, and we need to have a couple that we can switch between. And then there's no backing up. There's no reversing a change in a team, but we can move on and try something else. And if we agree to that, then great. We can let go of something that didn't work. Okay, example of an experiment in a team. My partner, Avdi, was consulting with this little company, and he's leading this team of developers, and there's one purple developer here who has been with the system. He wrote it over the last 10 years. He knows everything about it, and it's very easy for him to get stuff done, but he doesn't know how much he knows. He doesn't realize how interlocked his brain and this code is. And then we've got two relatively junior, new to this system developers who are trying to help. This is blue and green. And blue and green just can't get anything done. They're always stuck on needing to ask purple developer a question, or else they do it wrong because they don't understand. Okay, so Avdi has an idea for how we might be able to help with this. And I'm gonna take you through the steps of when I'm trying to be maximally experimenty with this, rigorous, when I'm trying to do a rigorous experiment in my team. I start with an observation. What is not as I would prefer it? In this case, blue and green can't get anything done. Everything's blocked on purple. Not cool. We would like to change this. And then there's a theory of what do we think is going on. Now, Avdi's theory was purple developer knows everything, and blue and green can't get traction on developing a mental model of the system because purple developer can change it faster than they can get any traction. This is normal. And then pause before you take any action and think about other ways you can test this theory. Do some deduction of, if this is accurate, what else would I expect that I can go look for right now? For instance, Avdi can take something out of the background. backlog. And you can go ask blue and green, how would you implement this? And they're like, oh, I know there's one part of the system we have to change, but I don't know what else and whether that would affect anything else, and I have no idea how to test it. And then you go to purple developer, and you would expect purple developer to be like, oh yeah, you just changed this one line, whatever. And so then you can test things at a very low cost just by asking people maybe a couple of hypotheticals or how they feel about stuff. That's really valuable. And then you get to what do you think you can do about it? And in this case, Avdi had an idea. He wanted the team to try ensemble programming. So ensemble programming, also known as mob programming, but ensemble is a nicer name. Everybody's in one room or one Zoom looking at a single screen. There is one person who's allowed to type, the driver, and you take turns. But the driver is not allowed to make decisions. All decisions have to be voiced by the rest of the team. So this means everybody knows why stuff is happening. Everybody gets the opportunity to ask questions. How did you know to go there? How do we test this? Oh, what about this other part of the system? Oh, I was going to delete that. It's not used anyway. I would have lost a week. And so why do you think that will work? Avdi had a reason, and it's because ensemble programming is maximized for spreading knowledge. You have all the knowledge of the team available to you collectively moving forward, which makes your forward movement incredibly smooth compared to single or even pair programming. And also, it gets that knowledge spread around. Now, in this case, he was asking the team to try something for 2 hours on a Friday. I heard about this at a conference and it sounded cool. Would have been a good enough reason. So that's also fair. But he did have a theory about why it would work. And then, before you do the thing, write down what you're looking for. Maybe you're measuring some things, but more likely, this is what might you notice if it's working. So like if it's working, we expect questions. We expect to hear, oh, I didn't know that. That's cool. We expect to hear dialogue between the team. And in the long term, we would expect blue and green to be able to work more independently. What might you notice if it isn't working? Well, if one person's typing and nobody's talking, why would we bother? That's not it. If blue and green are not asking questions, then this isn't working and we should try something else. And then what else to keep an eye on? Over the long term, because this like totally caught on, and the team actually loved it, and they like mostly ensemble programmed for months after that. And so at that point, you need to keep an eye on the throughput of the team, make sure it's not being adversely affected. Generally, it's much better because it's so much smoother to have all the knowledge in the room, and you never get merge conflicts when everybody's working on one thing. Yeah, so, but if you write this down beforehand and then come back and look at the results and also look for things you didn't expect, that makes this the most experimenty. That is rigor, okay? It's not a randomized controlled trial. It's not a controlled environment like systematic testing and measurement, but this is rigorous. The definition of rigor is different at the socio-technical level, and we can become fluent in that and we can become better at it. Retrospectives are like the one thing out of Agile, in my opinion. I mean, Agile mostly has been destroyed, but if you have some mechanism, and the retrospective is just the easiest mechanism, if you have some mechanism for observing, reflecting, trying new things, and then looking at the results, then you're going to get better. And in the medium to long term, getting better is way more important than being good. So retrospectives recommend. Oh, and shout out, the most versatile instrument at this level is relationships. Because if you can ask people, hey, how is this working for you, and get a candid answer, you can save a lot of work with experimenting on actions and stuff. And if people trust you to let you know what's going on that you didn't know about, then you can find surprise. You can see all the other results. So this is where just having halfway, just friendly, reasonably trusting relationships with most of your coworkers, makes a huge difference. There's a different talk about that. Okay. So this is how we can make our symmathesy even better. And we can learn together. We look at the results, we update our theory, we move on and try again, and as a result, we are changed. We become different. As the system around us is changing, we are changing too, and we're all becoming more compatible with each other and able to move forward. Okay, so if this works, oh yeah, here's the 4 levels, and here's the most versatile instruments, and now I can define experiment because I can define it at 4 levels. But then, if this works, what do we need to do next? They're going to ask us to scale it up. Well, no, let's make the whole company agile, where by agile we mean some formula of, no. We don't scale it up. Remember the iron law of evaluation. These experiments that work at a team level do not transfer because the situation is different. Copy the questions, not the answers. You can go through the same process in a different team, but the same answers will not get you there. And there's nothing that you can do to find some experiment that's going to work in every team. No, not a thing. If you want to make change at a level bigger than your team, if you want to make lasting change in your whole company, I can't tell you how to do that, but Beth can. So Beth Andersbeck has a talk that Z did at Agile 2022 that was not recorded, but Z made a video of it and put it online. It's $10. Please give Beth $10. If you want to make long-lasting change in your company, this is the only thing I've ever seen that really provides hope. It talks about how we can build new structures that are not from above, because a hierarchy can only build hierarchy. And we need new structures in addition to hierarchy, not instead. In addition to hierarchy, we need new structures that can reproduce themselves not by copying, but organically and adaptively, more like biological reproduction, and where we can get alignment throughout all developers in the organization, not conformity, because we're not enforcing standards. Instead, we're encouraging a fabric of norms. Norms are flexible in each situation because they're not rigid, but they're much stronger than standards because they're socially enforced. Right, Beth talks about how to do this. It's really good and really hard and really slow and involves a lot of meetings. But if you want to make change at the big scale, that's my advice. There is another way to think of scaling this up, though, that's not just in your company. We can think of scaling up the symmathesy of the learning together to involve all of us as an industry if we add another thing and compare our results with each other. Not just our results, but ideally, it's more rigorous if we tell people what we observed, the situation we were in, so we can get closer to the it depends, what we were trying to do, what we did, what the results were. If we tell each other stories, and that means informally, it means in Slack, it means in incident reviews, but also here, not just on stage either, in the hallway track. If we are comparing our results with each other and spreading this variety of experience around, then we're doing science. Because science isn't something a person does, it's something a culture does. And I think we're not terrible at it, and we can get even better. So everyone who blogs or makes a long Twitter or Blue Sky thread about stuff that happens, we're helping each other. And this is a different way of scaling our learning that's actually involves fewer meetings. But the symmathesy is where I always come back to. It's where I want to bring this learning, because this system grows when I maximize the flows of learning within it, the knowledge flow, and that's good for me individually and in my team. Comes back to everything is an experiment if you look at the results, reflect on them, and let them change you. If we really look at the results, we will be changed, we will know something new, we will be someone new, and that's a great thing. At the end, Here's a QR code. Probably has references.